Hello, my name is Andrew Kim, and this video is on TDR Explained. So TDR stands for Time Domain Reflectometer, and it's an instrument used to determine the characteristics of a transmission line by observing the reflected waveforms. Inside of the TDR, there is a voltage source that is super heavily regulated. There's also an impedance that is matched towards the cable, so there's no reflected, and we'll kind of talk about that later. There's a switch that's also heavily regulated in order to kind of switch on and off. And at the very end here, there's a voltmeter, which is what is reading right here. That's voltage, and it'll show us the reflected waveform as it comes back. So there's two concepts that we should know about transmission lines before we kind of go into the TDR, and that's delays and reflections. So I guess simple enough, a transmission line will have an associated delay with it. So a signal that goes on at the end will take some time, or a period, which is what we're going to call it, to reach the other end. And then there's also the concept of reflections, where if there's something at the end, it'll reflect back a voltage or send back a voltage that is kind of unique to what is at the end of here. So we'll kind of go into that right now. So our two cases we're going to talk about is open circuit and a short circuit. And in both of these cases, we're going to assume that Z0 is ZG, like in the TDR. So I guess right here is our TDR, and right here on this side is our TDR. And then on each side, we have an open circuit on this side and a closed circuit on this side. So in the case of an open circuit, we see this is kind of what the TDR will see, and it'll send a half VG signal, which I guess in every single case, in our cases at least, we'll be sending a half VG signal. And then the voltage will travel all the way down the line, and then it'll reflect back the same amount, and then it'll travel all the way down the line again, and then TDR will see that extra amount. So it goes from half VG to the full VG. In the case of a short circuit, the TDR will send out a signal, half VG again. It'll go all the way down the line, all the way back, and then it'll just drop down to zero in the case of a short, because the short will send back a voltage that is negative half VG. So these two kind of graphs we want to keep in mind as we go into the next examples. So next is case one, where instead of having an open or short, we're going to be having a resistance of some sort. And in this case, our resistance is going to be 2 times the value of Z0. And so we're going to use this reflection coefficient, which is basically going to be Z minus Z0 over Z plus Z0. And this is the kind of the percentage of the wave that's coming in that gets reflected back. So in this case, it's 1/3. So in our graph, we see that we get half of VG sent down. It travels all the way down the line. The 1/3 of half VG gets sent back. And then we see this increase in voltage at the TDR side. So something to keep in mind is that if Z was less than Z0, then we would actually see a drop in voltage because it would have a negative reflection coefficient and then reflect back a negative voltage. So here in case 2, we have a capacitor on the other side. What we can see is that a capacitor, in our knowledge, we know that uncharged acts like a short, and charged, it acts like an open circuit. So what we'll see here initially is that it acts like very much like a short on the TDR side. So it'll go all the way, it'll send it to half VG, go all the way down, travel all the way back, and then drop to basically 0. But then after that, it's going to kind of transition into this charge state. So since the capacitor kind of does this this curve kind of graph, we're going to see that it goes all the way to VG as if it was an open circuit as time continues. So in case 3, we have an inductor on this side, and it basically acts like an opposite of a capacitor. So initially it's going to be open, and then after a while it's going to be short. So we have our open circuit, so it goes half VG, and then it spikes up to VG, or just about it. And then after a little while, it's going to go all the way down to about 0 voltage. In the next part, we're going to be explaining or going into a more complex example and kind of going into all the mathematics behind what we should be seeing in a TDR. So in this part, we have a TDR on this end right here, and then we have this complex circuitry on the other side. So we see we have a transition line, some circuitry right here, so it's a capacitor and a resistor, and then we have another transmission line and another impedance on the other side. And then we're going to assume that ZG is equal to Z0 as in our TDR cases. So first thing we're going to do is kind of go over the first voltage wave that goes down, and we know it's half VG since from our previous examples, as well as the mathematics behind it is kind of a voltage divider between Z0 and ZG. As we continue on, we're going to go over some kind of damage control basics. So we're going to go over the reflected waves on each side, And we're going to know that the reflected wave on the generator side is going to be 0, as our TDR property stated. And then we're going to know that the reflected wave, reflected coefficient on the load side, on the Z0 side right here, is going to be also 0, and there's the math behind it. We're going to do Z0 minus Z0 over Z0 plus Z0, which is going to be equal to 0. And so that means as we go into our analysis, we kind of ignore anything that goes from down this way or from this way. All we have to worry about is things that get reflected back this way and then reflected around this way. And now we're going to go ahead and split this circuitry right on this line. And on the left side, we have this circuitry right here, which is the transmission line, and then the TDR. And we're going to simplify that to this case right here, which has some mathematics behind it, but in general, a group like this can be simplified in the Thevenin equivalent to a 2V plus, which we calculated up here, and then a impedance value that's equal to the transmission line impedance. And then as we know that, and since we know there is no reflected wave on the load side, we can also simplify the right side of the circuitry to be this right on this side. And that's because since there's no reflected wave, there's no real change in voltage, so all the voltage divider kind of works out in the end, and we can kind of redraw this just as simple as that. So there's our new circuit right there. And now we're going to keep doing some Thevenin equivalents to kind of simplify this into a really basic form. So right here, we're going to be switching this capacitor and this resistor around in order to get these 2 points and then do the Thevenin from these 2 points. And what we see here is we get our voltage through this equation, and this is our result. And then we get our Thevenin resistance, which it goes through this math right here, and we get this result. And so I guess you can take a look at the math, but overall, the end result is going to kind of look like this simple RC circuit. And now we can go into the RC circuit analysis. So as we do our circuit analysis, we come up with this equation as we go down, and then we also know that the current is equal to C dVc over dt, and Vc, we're going to say is going to be the voltage across the capacitor. So as we work at this equation, we're going to kind of turn it into a linear first order diffie-q. And then as we continue to work on it, we get this version, and then we can use the kind of differential equation solving form to get this equation right here. And then we have our tau constant, which is 0.615 Z0 C, and a period t, which is the time it takes for it to travel down the line. So now we know that the voltage at the capacitor will be equal to this equation. And then we also know that this voltage, since the capacitor is linked directly to this transmission line, that the voltage on this transmission line will equal this value as well, but we don't really care about that in this case since we're only doing a TDR analysis. So this next part, we're going to be looking at this junction now. So we're going to go back to our original new circuit and then kind of use this equation and plug it into our junction equation. In this step, we're going to be taking the 2V plus and then kind of subtracting it in order to find the voltage at the junction. And so as we keep solving it out, we get this, and we're simplifying 2V plus to just Vg, since we know that V plus is just half Vg. And so the final result is we get this. So at the junction, depending on the time, we get this overall voltage. So in the end, what that really tells us is that since it takes the junction voltage t time to go all the way back down, all we have to do is really delay that voltage by t, another t, and then we also know that the voltage on the line will equal that half Vg value that we calculated at the beginning for all the time it takes to go down the line and back. So at the end, we have V plus and then the original voltage for 2t. So this is kind of a representing that from time 0 to time 2t, we're going to be having a value of V plus. And then after that, we have this delayed by 2t here and here, and that will be equal to, the voltage will be equal to this at the TDR side, and where our tau constant is going to be equal to 0.615 Z0 C. Overall, in this simple analysis, I guess if you want to just plug in the numbers at this point, you could really solve for what time and kind of analyze what the capacitance is and kind of detect what is on the end of the line and do TDR analysis. And with that, our overview of TDR is over. Thanks for watching.